Good morning, good afternoon, or good evening to everyone, and thank you for joining today's webinar. My name is Todd Luxton. I'm a research chemist with the United States Environmental Protection Agency, Office of Research and Development, and I will be the moderator for today's webinar, What We Know About NanoEHS, Nanoinformatics, and Modeling. The NNI's NanoEHS webinar series focuses on sharing what we now know about environmental health and safety aspects of engineered nanomaterials. This webinar will feature experts from diverse disciplines to share their perspectives on key findings on this topic. Today, we're going to be featuring nanoinformatics and modeling. Before introducing our excellent panel of speakers and providing a very brief overview, I want to mention that the NanoEHS webinar series is an important platform for agencies participating in the National Nanotechnology Initiative, the NNI, to share the information on NanoEHS research progress and findings. Throughout the series, experts will share the big take-home EHS messages with the broader nanotechnology community and highlight the NNI's role in answering those questions. We have set aside time for your questions to the panel today. You can type your questions into the Q&A box located at the bottom of your screen, and we will try to get through as many questions as we can. I look forward to a lively conversation, and let's briefly introduce our speakers for today. Our first speaker is Andrea Haas. Andrea is the head of the Fiber and Nanotoxicology Unit in the Department of Chemical and Product Safety of the German Institute of Risk Assessment. A biochemist and a toxicologist by training, her work since her appointment as the unit head in 2008 has addressed the integration of nanomaterials in different regulatory frameworks in the EU and conducting nanosafety research. Dr. Haas has been involved in several large national and European nanosafety governance projects and is the co-author of the EU-US Roadmap for Nanoinformatics 2030. Our next speaker today is Stacy Harper. Stacy is a professor of environmental engineering at Oregon State University. There, her lab has worked on developing and applying rapid testing strategies to investigate tools to determine potential hazards of nanomaterials and nanoplastics and link those to the material properties. Dr. Harper has spearheaded the development of a knowledge base of nanomaterial biological interactions between OSU and the Oregon Nanoscale and Microtechnologies Institute. Next, we have Fred Klassig. Fred is a manager of the Pennsylvania Bio-Nanosystems and co-chair of the US-EU Database and Computational Modeling for NanoEHS. Prior to this, Fred was the technical director and business director for the Aerosil line at Invoke Dagusa. This work led to his involvement in the international standards and development organizations such as ASTM International and ISO, as well as industry-led organizations. He is also the co-editor of the EU-US Roadmap Nanoinformatics 2030. And finally, we have Robert Rollo. Robert is a director of the Physical and Computational Sciences Division in the Advanced Computing, Mathematics, and Data Division at the Pacific Northwest National Laboratories. His research interests are data-driven analysis and modeling of complex systems. Prior to joining PNNL, he was an associate professor in computer science and artificial intelligence and director of the Advanced Technology Innovation Center at the University of Rova Virgili in Canatoli. Dr. Rollo has served as the chair for the modeling, WG and EU Nano Safety Cluster, and as the EU co-chair of the US-EU NanoEHS Human Toxicology Community of Research. Now, just one final comment before I turn it over to the panel. I hope that you will join us for the other NanoEHS webinars in the series. And more information on all of the NNI public webinars can be found on nano.gov. You can also follow us on Twitter at NNI Nano News. And so with that, we will turn it over to our first speaker, Andrea.
Okay, thank you, Todd. Thanks for the kind invitation and for the nice introduction. And it's my pleasure now that I can provide an overview from the European perspective. Let me just see. I think now you should be able to see my slides. So I entitled my presentation, What Do We Know about Nanoinformatics? And I intend to give you some insight from selected European projects. Of course, it's not a complete list, also for time reason. And there are some logos already depicted here, but I will guide you through. Just let me start with a general introduction. So I entitled that Nano Safety, Where Are We? And just starting from the application of nanoparticles or nanomaterials, I think we are all aware of the fact that nanomaterials are used nearly everywhere. So there are plenty of applications already on the market and many more are under research and development. That means nanomaterials are very complex. We have a lot of different chemistries. We have plenty of forms and variants. And moreover, not only that each of these nanoforms can behave differently, also in addition, we need to consider complex changes of these materials. And this picture here is just a simplification. The reality might be even more complex. So there might be dissolution, agglomeration, heteroagglomeration, changes in the surface chemistry and other properties in reactivity, and so on, nanocorona, and so on. So all of that renders the material characterization and also a proper dosimetry highly challenging. And to sum that up, I think we urgently need modern data-driven approaches to deal with the complexity of these materials, as not each and every variant in each and every modification can be fully tested for each and every endpoint. And so we have that modern data-driven approaches, be it AOP-based assessment strategies or integrated approaches to testing and assessment, or safe by design, safe and sustainable by design. All of these modern data-driven approaches, they have one aspect in common: they need data. A lot of data. And so, of course, the knowledge has increased dramatically in the last decades. So knowledge is further increasing and plenty of information is available. We have a couple of nano-specific databases or nano-safety databases. We have a couple of other relevant databases that partially store also relevant data from the side of nanomaterials. There are other useful resources, like for instance, Zenodo or Figshare, where some of the authors may deposit their data sets in parallel to the publication. So that means from the perspective of a user, many challenges remain. How can you find relevant information for your material or your application? How can you evaluate the relevance and the reliability of that data? And how can you bring together all these different pieces of information? So that means the solution in our perspective, and that's not only my opinion, this is also coming from a couple of collaborators from different European projects, we think we need to push forward towards a fair data infrastructure. So what do these letters mean? Fair is the abbreviation for making data findable, accessible, interoperable, and reusable. And behind each of these aspects, there are a couple of issues, and for time reason, I only would like to emphasize the most important issues. So for instance, to make data findable, the data needs to be enriched with metadata and needs to be assigned with a unique, globally unique and persistent identifier. Yeah. Then for making data accessible, also the metadata need to be accessible, or in particular, the metadata needs to be accessible even if the data set is not accessible or no longer accessible, so that at least the information can be obtained, that the particular data set is available in a specific database, such that then access permission can be checked out. For the interoperability, it is important to use formal, accessible, shared, and broadly applicable languages ontologies. And for making the data reusable, it is of utmost importance to have clear and accessible data usage licenses. Yeah, so, and this is not the completeness, this is just like the important issues. And also, we need to keep in mind that making data fair by no means means that the data is open and that each and everybody can just use it for any purpose. So this needs to be clarified and emphasized as well, because otherwise people may be reluctant to publicly share the data sets. And this is an issue that actually has been initiated in a project where I had the pleasure to participate in NanoEHS 2. This is the publication that came out at the end of the project. We put together our perspective, how the nanosafety data infrastructure can become more fair, and we shared the experience that we made in this project, where we reached out to other Finnish projects and we collected complete data sets of these projects and incorporated them into a nanosafety data interface based on eNanoMapper. And as you can see below, this is the current view of this interface. So meanwhile, many European projects are using this interface. So we think we can say it's one of the largest nanosafety databases that we have worldwide, and you can access it via this link here. And specifically looking at the NanoEHS 2 dataset, you can see an overview here. So this is only a tiny fraction of that whole interface. This is only the NanoEHS 2 database, and you can see here the number of data points and the number of methods being represented in the database for particular forms of nanomaterials. And you can see here then which of the nanomaterials are mostly populated in this database. So this is titanium dioxide, for instance, silicon dioxide, multi-wall carbon nanotubes, zinc oxide, silver nano particles, just to mention some of them. However, we also experienced in particular issue for some of the data, such as omics data, as very often omics data are stored in specific repositories that are not nanospecific. So, and even so, these omics data overall have a very high FAIR index. Since the nanospecific descriptors are missing, this is hindering the reuse of these data for the nanosafety community. And so this is something we initiated already in NanoEHS 2 by linking transcriptomics data sets. And this is currently ongoing also in other European projects where we try to link the data sets in specific omics repositories then to eNanoMapper. And this is something that we addressed also in a reply to our publication. And you see below that actually the NanoEHS 2 database overall has a very high fairness score. So in the project Gov4Nano, this is something that has been taken on and pushed to another level, and a fair implementation network was established. I will not talk you through this complex slide, but the idea is that we would like to develop a fair data ecosystem that allows the various stakeholders, be it citizen, policymakers, industry, researchers, and the civil society, to get access to high quality, trustable data. And this advanced nano implementation network has been established under the Go Fair initiative. And we also released a video that is available here via the link that explains the idea behind this initiative. And a couple of case studies are currently ongoing. Some of them are initiated by Gov4Nano, and some of them are initiated by an infrastructure project, Nano Commons. And just to name some of them, so there is work ongoing on persistent identifiers, on the use of electronic laboratory notebooks to upload data more elegantly and easily. However, we experienced that basically the biggest challenge here on the way forward is how to stipulate the researchers to deposit their data in such infrastructure. So we think the largest bottleneck is not on the side of the technology, but rather how can we change the mindset in the community. And I would like to emphasize before I end two other aspects that I find highly important. This is the standardization of metadata. This is also really important to make the relevant information findable and to make data that is stored in different databases also interoperable. So this is just giving you a general idea. So if you have an experiment ongoing, there is a user and operator, there is some detection or measurement ongoing, but before there is some sample pre-processing, the equipment needs to be described, maybe there is a calibration, then there will be raw data, and then you have a property that is measured, and then there's data analysis and post-processing of the data. And for all of that, we need metadata that truly describes what has happened to that specimen or to the nanomaterial. And that is highly challenging to make that in a standardized manner. And this is an initiative that is currently ongoing in the project NanoCommons. So for time reason, I will not talk you through this very complex figure. But the idea is, maybe just going one step back. So basically that we work with archetypes. So we have archetypes for the instrument, for chemicals and so on. And so all of that should contribute to a standardized metadata description. And what is also needed from the perspective of a user, you don't only need the data, but you need tools to analyze the data. And this is another example from NanoCommons, where basically tools are developed that are then directly linked to the data infrastructure. In this example, it's NanoExtract, it's a nanomaterial image analysis tool. I will not talk you through. If you have questions, please feel free to ask me later on. And more work is ongoing in other projects, like also in NanoCommons, they have other tools, Nanoinformatics and NanoSolve IT. So that brings me to the end, and I hope that I could convince you that, first of all, the digitalization is highly important, as this will enable and advance data-driven approaches that are urgently needed for the hazard and risk assessment of nanomaterial, but also to ensure safe innovation. Yeah, and I tried to give you some insights from selected European projects, and I would like to emphasize here on this slide the Advanced Nano Implementation Network. You need the different stakeholders to buy into this idea, and we need to foster a fair data landscape. Also, there are challenges as more material types need to be represented. And this is an example. So currently ongoing project like Harmless focus on multi-component material. Polyrisk focuses on micro and nanoplastic. We need to integrate information from different databases, like I have shown you with the omics data, and we need tools supporting the digitalization, the easy upload and the easy reuse of data. Example here is a Gracious template wizard that has been established from Gracious, or the NanoCommons electronic laboratory notebook case studies. And of course, I would like to thank many collaborators coming from all of these projects for their valuable input. And later on, I'm happy to answer your question. You can already paste them now in the Q&A box. Thank you at this point.
Sorry, Stacy.
That's okay. I think I'm on now. I didn't know if you were going to introduce or not, Todd, but
I thought that I had, but I was on mute.
okay, well, here I am. And for those of you that are on that I haven't seen for a couple of years, howdy, I'm still here. And I really appreciate you guys bringing back, at least getting the gang back together for this panel. I think it's been fun just working through how we were going to do this. So I'm going to focus my remarks today on what we can draw from the wealth of NanoEHS research that has been conducted over the past decade and a half, 2 decades, and what we can really leverage to inform some of these new materials that Andrea was just talking about, and specifically in my world, nanoplastics. So when we started this over a decade ago, when we were writing the Nanoinformatics roadmap, the US-based one, we really envisioned a path in which we could advance NanoEHS research by basically leveraging nanoinformatics. None of us, we were just talking with Todd, the panel was, and none of us are nanoinformatics people per se, but we're researchers who saw the need for nanoinformatics in really advancing our understanding of nanomaterials and getting to that holy grail of thinking about, can we predict a material's behavior just based on the physical chemical properties of it. And so this was like, the Wild West. This was when, we were collecting few studies that were collected and reported information on things like agglomeration state, which we now know is critically important. There wasn't much consideration given to instances of characterization. So thinking about, when in the material's life cycle, this was, the data was collected, and that's important because we know that transformations can occur. So this was kind of what our data pipeline looked like, and it was literally a pipeline where we would collect data, everybody doing their own independent research, collecting data, processing it, analyzing it, writing up your publication, and then curators on the backside would have to go in and extract that information back out of publications. And a lot of negative data is missed that way, or not reported on, and then wouldn't be considered in a final risk assessment. So is quite biased in some ways. And then the computational analysis of curated data could happen. But what we did is back then we envisioned what it could be. And in Andrea's overview of the EU's efforts, these data repositories, our real pie in the sky idea was a set of interoperable system of federated databases that could share information and making sure that information was the same. Now we still have the same old pipeline here where you collect your data and then you publish it, but by putting that raw data annotated so that people can understand it and understand the error and variability in the data, and be able to share like materials with other like materials. And in this way, drive, hopefully some predictive models that Robert will be talking about, and even inform, the next round of study designs. So in order to do this, to support this effort, the National Cancer Institute's Nanotechnology Working Group led an effort for several years where we were trying to adapt this standardized tab delimited format that was developed by the European Bioinformatics Institute. And we were trying to basically adapt it so that it could describe nanomaterials, because just the complexity around describing a nanomaterial is so immensely complex that we really needed some assistance in thinking about what that was and working through it for all of the different nanomaterial classes. So we basically added a materials file extension onto this ISATAB format. And I believe that is the basis for most of the EU efforts. It was at least the starting point back in mid 2015 or something like that. And so this basically allows us to catch all of those critical physical chemical properties and complexity about a nanomaterial, not just the surface chemistry, but how that surface chemistry is actually attached. And we moved this forward to an ASTM standard to make it useful for other people. Now, for informing nanoplastics risk, many of the engineered nanomaterials that are on the NanoEHS research have been, are commercially available, or they can be synthesized in small batches to tweak, a specific physical chemical property that you want to. I think my last look at the Nanocomposites website for ordering materials, they have like 23 pages of options, and that's not adding in any customization that you could do. So a lot is available. nanomaterials themselves can be precisely engineered for their shape, for their size, for their surface chemistry, and they're oftentimes available in homogeneous suspensions. So we can study these to determine what are the factors that are driving, you know, their fate in the environment and also their impact on living systems. Most engineered nanoparticles or nanomaterials are produced at the nanoscale, and therefore the primary particle size is within that nanoscale. Whereas only a few nanoplastics are generated as primary particles, and those are limited primarily to polystyrene and PMMA. Most of the nanoplastics that we're dealing with in the environment are going to be a result of breakdown of macroplastics to microplastics to nanoplastics. So we can say something, from the microplastics research, we can say something about potentially the occurrence of these materials. If you look at the breakdown from macro scale plastics to microscale plastics, that same trend of the ratio of the different types of plastic that are more prominent should hold at the nanoscale as well. A good hypothesis nonetheless. So those materials that are commercially available, the polystyrene and the PMMA, are only available in spherical forms, which is clearly not what we see or will see in the environment. In addition, the surface chemistries are pretty limited to, you can get a positive charge by adding some amine groups, carboxyl groups to give it a negative charge, or it could be left, undecorated and just be neutral. But this really limits the information that we have on nanoplastics effects, and certainly can't be doing the comparative types of studies we've been doing in NanoEHS. So what can we draw from that NanoEHS to inform plastics risk assessment? And I would say all of these environmental transformations that were described eloquently by Greg Lowry in his 2012 paper should hold for nanoplastics, right? I guess here where we have dissolution, that would not necessarily be the case for nanoplastics because they're persistent and they don't dissolve. And the transport through the environment will likely depend on agglomeration state, just like it does for nanomaterials. And both of these processes should be affected by things like salinity, pH, organic matter in the system. So we know a lot that we can draw from. The formation of the organic matter layer in the environment or a protein corona in a living system should also, be the same if the outermost surface chemistry is the same or similar enough. And transport, then we could think about that, could be similar to nanomaterials if they had the same density. So if you think about, nanocellulose or nanolignin, both of those might have a density that's similar enough to nanoplastics to be useful and informative. On the environmental fate and transport, both in terrestrial and aquatic systems, these should also be comparable if they're in an aqueous system, the density is going to be a big driver. And as these particles agglomerate, plastic particles, even at the nanoscale, may, float after they agglomerate, as opposed to falling into the sediment like you would expect from metal nanoparticles. And if they're unagglomerated, they can really remain suspended in water bodies indefinitely and lead to exposure to organisms that live in or traverse through the water column. Again, there would be no, dissolution of these plastics, but there have been some concerns about leaching of some of the additives and the stabilizers from the plastic particles. And I think a good example of this is the 6-ppd quinone that's released from tire wear particles. For environmental sampling and quantification, I think we have the same issues in environmental sampling that exist for nanomaterials and nanoplastics. And these would be things like difficulties in collecting them, right? For microplastics research, they're not even trying to get down to the nanoscale at this point. But also concentrating the samples. There's interference from the colloids in the system. And it's really challenging to try and locate them once they're in a complex matrix. Now, dynamic light scattering and things like nanoparticle tracking analysis can be used for both nanoplastics and nanomaterials. But since both instruments really rely on the idea that the particles are spherical, the vast majority of nanoplastics are going to violate this assumption, while many of the engineered nanomaterials are engineered to be spheres. And one other thing to note is that some of the clear plastics evade the detection system for nanoparticle tracking, at least. Some considerations. So thinking about, uptake and translocation, what can we glean from NanoEHS? I think the mechanisms of uptake would be very similar, particularly when you think of this mechanism being a function of size. So the smallest nanoparticles here can directly penetrate through cell membranes. We have particles that are around 100 that can, get in through the clathrin-mediated endocytosis. We have 50 to 80 nanometer ones that can get in there using calvula receptors and endocytosis. And then those that are larger ones will be mostly taken up through phagocytosis. Now, one other consideration, or a couple of other, is the biodistribution, again, should be similar if the particles have the same size, shape, and charge, or close enough, right? We need to know what that distinction is so that we can start reading across. But the accumulation of nanoplastics could occur in lysosomes because they will not break down even at the very, very low pH environment that is found in the lysosomes. So that could be problematic. So lastly, I wanted to touch on what we know about the toxicity relative to NanoEHS. And reactive oxygen species generation is a predominant finding for both nanomaterials and nanoplastics. Although right here where the nanoparticles, some nanoparticles themselves, especially the transition metals, can generate ROS on their own. It would be my hypothesis that the nanoplastics would do the oxidative stress through the cellular interactions. And particle-specific effects would be expected for both nanomaterials and nanoplastics. The three main things that have been indicated for both nanoplastics and nanomaterials toxicity are inflammation, oxidative stress, and metabolic disruption. So those are kind of the highlights. And lastly, I want to end with my slide on nanoparticle safety testing to share with you all. And with that, I will hand it over to you, Fred.
Thank you, Stacy. I'd like to thank Todd for the introduction earlier. I'd like to thank the audience for participating or being here. And I'd like to thank Kristen Roy, who's going to make certain that my slide presentation goes flawlessly. I'm going to be describing the role of dissolution in current risk assessment models for oral ingestion. Dissolution is an intriguing phenomenon, as the dissolution will limit the amount of particles that are present, and for toxicology, with dose makes the poison, that can simplify testing considerably. In 2011, when the NanoEHS plan came out, the concern was the particle effect. And what I would say there is, was the toxicity observed the particle? Was it the dissolution products? And when one goes through the plan, you'll see that there are milestones for test method development, for applying those test methods to silver, which was the case study. And there's a chapter on informatics, which combined all of these results into a coherent data set. This continued in when Stacy and I and others were working on the first Nanoinformatics roadmap, but the situation changed somewhat when we got to 2016. And can I have the next slide, please, Kristen? When Andrea Haas and I began our work on what eventually became the EU-US roadmap. There certainly in the intervening years have been more reports on nanoscale particles dissolution, but there was also divergent regulatory opinions. And I'm using here hydroxyapatite as the case study. It's the mineral form of calcium phosphate found in bones and teeth. Paul Westerhoff of ASU had documented that NanoEHS was present in baby formula for sale in Australia, which led to a review by the local authority, Food Standards Australia and New Zealand, who took the position that it would dissolve in the stomach, therefore no exposure, therefore no action. In Europe at the same time, around 2016, the Scientific Committee for Consumer Safety was concerned about, also addressed NanoEHS in toothpaste and mouthwash. They expressed concern about oral safety, but did not address dissolution as an effect that should be considered. So for Andrea and myself, there was an opportunity, progress in literature, divergent opinions, could we bring them all together? And we put this together in a pilot project in the roadmap, and I've repeated here what our objectives were there, but they really come down to identifying stakeholders, bringing them together, and then seeing if we can make advances accordingly. Next slide, please. There were, of course, technical reasons that justified such a project, but in the background, I would say we are dealing with the fact that it was a topic that would unlikely raise issues regarding confidential business information. And that means that we could focus on what I call the fourth point here. How do you do test methods that simulate physiological conditions, the solution characteristics, the compartment identity, and the residence time, such that the resulting data are useful from a toxicology standpoint? And certainly that is the area where I've been engaged with and have learned from in my interactions with NSF International, who are a public health standard development organization for testing products, certifying them, and then auditing them for the use in potable water systems. Next slide, please. So let me kind of give a concrete example. Lead pipes are used in a number of municipalities in the United States. You're supposed to feed phosphate to maintain a phosphate barrier layer. And in Flint, the budget was cut. They stopped feeding phosphate and corrosion occurred. And there's a question of whether or not people are being exposed to particles or to soluble lead ions. What I have here is a chart from dissolution study for galena, which is lead sulfide, an insoluble form of lead. And you can see that as it dissolves in gastric fluid, these two curves reach the same plateau. We can assume equilibrium. To the right of that vertical line I drew, and to the left, you can see the approach to equilibrium. Smaller particles reaching equilibrium faster than the larger particles. In essence, the equilibrium's to the right, the kinetics are to the left. And if you ask me my opinion on 1 or 2 ppm of particles in water, I would say that they'll probably dissolve in the stomach, and therefore your exposure is to soluble lead salts. Of course, that has to be demonstrated. Next slide, please. That's not always the case when it comes to nanoscale particles. What I have here is cupric oxide, tenorite, and you see on the left that the plateaus for this material change with the shape. So spindle is the bottom, rods are the red line, slightly higher, spheres are the higher line. So in this case, the plateaus do not align with the equilibrium, and you have, shall we say, effects of the particle shape. On the right, I have concentration, same particle, different concentrations, and I've kind of provided on the right-hand side what the solution concentration was. These profiles are completely kinetic. There is no equilibrium branch, and you can go to references for nanosilver, for example, where the same is true for those particles. Size leads to different plateaus, the dose level leads to different plateaus. And this naturally raises the question of what is a possible explanation. And then I go to the next slide, please. I'm now into the world of geochemistry, which is one of the reasons I've been saying mineralogical names. This is albite, which is a sodium aluminum silicate. And draw your attention to the picture at the right, a relatively smooth surface. There's some lines that represent ledges. And when you do a dissolution study, you're monitoring or measuring the retreat of those ledges, or their movement across the field of view. On the left-hand side is a similar material, but it's a rougher. There's etch pits present. Dissolution now is on ledge movement plus the formation of etch pits, the number of etch pits, and whether the etch pits actually grow, or how fast they grow. And you can see that these authors have aligned this with 2 different mechanisms. based upon the level of undersaturation. And undersaturation is the solubility product re-expressed for activity. So what happens in a static system or a batch mode test, you start severely undersaturated. As the particle dissolves, it starts moving to mechanism 1, and where it lands starts depending upon how it was manufactured, or as we would say, engineered when it comes to nanoscale materials. Did the manufacturing process introduce line defects, point defects, screw dislocations, and the other sorts of elements that come with the crystal growth? But I want to point out that this is for a flow-through system, and the previous work was for a batch system. Can I go to the next slide, please? This is a series of data from flow-through testing on silica particles. Everything on this page is a silica particle, and surface treatments may differ. Orange is a lung simulant fluid, Gamble solution around pH 7.4. Black is a lysosomal acidic solution around pH 4.5. And you can see that the shape of the curves differ. On the left, the orange is more likely to have curvature. On the upper right quadrant, relatively linear reactions there. This is somewhat confirmed if you look at the where I drew the circle. Those are the 3 materials that did not have any surface treatment. They're somewhat together when it comes to the pH 7 neutral material, but they separate when it comes to the acidic material. Obviously, the kinetics have changed. When you combine these 2 conditions, you somewhat simulate the lung. So that's one of the reasons that this work was done. But what's missing is any plateauing or any asymptote formation indicating a limit. And that somewhat makes sense because this is flow through, the undersaturation is controlled, and therefore you can go to completion more readily. Have the next slide, please. So I just like to somewhat recap. In 2011, the concern was a particle effect. The actions taken were appropriate. 2016, people are used to the fact that there will be mixtures, and those mixtures will change in their relative composition based upon the physiological compartment that you're considering. When you do batch mode, you're probably seeing undersaturation decreasing with time. Asymptotes are more likely to be visible, and they may be sample specific in terms of shape and size. And this testing is probably better attuned to compartments, the stomach or phagocytes. When it comes to flow-through testing, on the other hand, undersaturation is fixed over time. Dissolution is more likely to go to completion. It simulates open systems where fluid is refreshed, such as the lung lining. The bloodstream is of other possibility. But in all of this I've talked about, the current use of kinetic reaction rate laws to describe the data is disconnected from the degree of undersaturation thermodynamics, and that represents the different interests of the disciplines, geochemistry versus what we're doing in NanoEHS. And the next slide, I'll finish just by what the current, regulatory climate is. Australia has not reconsidered things, so that's a historical number comment. But in Europe and the United States, we're seeing a movement towards dissolution in the stomach. If it's complete and it's demonstrated, then there's no systemic exposure. Localized genotoxicity testing remains required. The European Food Safety Authority has provided test conditions. Those are batch conditions, 30 minutes and stomach acid, less than 12% remaining at the end. And in the United States, NSF International, they have extraction tests to determine the drinking water concentration of a nanoform that comes from a product that is being used. And then the second step would be dissolution in the stomach using the EFSA conditions, and finally in vivo genotoxicity. So there's been progress. At the same time, there are challenges. And the next slide, I would again like to thank the audience for watching. Good day.
Thank you so much, Fred. And we'll have our final speaker now, Robert.
Thanks, Todd, for the introduction. And thanks the organizers for the invitation. So I would like to focus in this last part of this webinar on an aspect which is complementary to what my colleagues have focused before, which is essentially looking at this nanoinformatics ecosystem and targeting the right side of this diagram that you see, which is, okay, we can generate data, we can use characterization capabilities to generate this data, and then we have computational approaches to model or to analyze this data, which is what at the end of the day helps researchers to get new insights from this data in this specific field. So since 2010 up to now, a lot of things have changed in the modeling field, and starting from the pioneering efforts in the US, for instance, in centers like USCIN at UCLA, or through different projects funded by the European Union within the FP7 and Horizon 2020 programs, we started to look at the translation of structure activity relationship for chemicals to the nanoparticle world, right? And in these pioneering efforts, we realized that the translation is one, not easy and not direct, because essentially, oftentimes the interactions with the biology, when we are talking about nanomaterials, is much more stronger, much more complex than what we have with regular chemicals. Also, the data that we are able to generate in the nano space is more difficult to generate, although by leveraging high throughput screening facilities, when we can generate larger volumes of data, but still data continues to be a limitation. So what I want to focus on this part of the talk is essentially on what has changed since then, and what are the challenges that still remain, and what are the opportunities that new modeling and new computational approaches offer to us. And I want to focus this talk in 5 different areas. One is, we have focused a lot in the past in the reproducibility of the data, but we need to focus also on the reproducibility of the models that we generate. The second one is, data alone is not enough to create this model, so we need to find ways to provide some domain awareness and to leverage this domain awareness within the modeling workflows. Then we need to make sure that these models can be, at the end of the day, used. So we need to make sure that these models are robust, that we can trust the predictions that we get from these models, and essentially that we can deploy in an operational settings these models. And finally, the last aspect that I want to cover is this idea of how we can advance in terms of having a much more tightly coupling between the modeling, the characterization instruments, and the whole scientific discovery process through automation and autonomy. So in terms of reproducibility, it's important, and it's still a challenge, to track the provenance of the models in the same way that we are tracking the provenance of the data. And this becomes more and more important, especially now with all these deep learning approaches, in which we have these huge scans of large hyperparameter spaces to tune the models. And if we are not able to keep track of all these processes, we may end up in a situation in which we can have models, or we can introduce inadvertently some biases in the model development process. So essentially, as we are moving towards this idea of AutoML using automatic methods to generate or to improve the quality of the machine learning or the data-driven models in general, we have to keep an eye, in the same way that we have done in the past, developing ontologies, developing curation strategies for data. We have to keep an eye on the reproducibility aspects of the models. The second element is this idea of domain awareness. So in most cases, we still have limitations on the data, and most of the modern approaches like deep learning are really data hungry. So they need lots of data to really have reliable predictions. So we need to advance in developing models that can operate in this fuzzy space in which we have data, but we do not have perhaps sufficient data, right, to develop a model that we can really trust. So in this space, again, and this has been addressed in the past when we were developing QSARs for chemicals, the validation of these models is essential, and understanding when the model is interpolating versus extrapolating. So when we are operating within the application domain of the model versus when we are not, is going to be extremely important. And this information has to be provided and has to be linked to all the modeling approaches that we implement. The idea of knowledge embedding with novel modeling architectures, we can start thinking on complementing the data with what we know about the biology, about the chemistry, about the material science aspects of the systems that we are trying to model. And this partially can help us, one, alleviate this situation of limited data, but more importantly, it can also increase the confidence that we have in the models, because we have some sort of physicochemical constraints that really control the response of the model when we are especially operating outside the applicability domain of the model. So approaches like transfer learning, reinforcement learning, and we have seen the advances, especially in reinforcement learning, with all the developments that Google with AlphaFold and other techniques have shown recently, right? These are really promising approaches that can help us to advance the field. Causality is another important element. So we and links with this idea of data is not enough, in which we need to really find the proper. We really need to embed the proper causal structure within the model, just to make sure that everything in the model makes sense. Robustness is again an important element, and one of the things that often are not taken into consideration is the bias that we may introduce when we are designing the experiments to capture the data and to generate the data. So bias, together with interpretability of the models, with explainability of the models, is something which is going to be key, and this is something which is a really important area of research that will have huge impacts when we are modeling the behavior of nanoparticles. And then with respect to the scalability, of course, with the advances in computing environments, we are in a better situation to start doing things which up to now were much more difficult to implement, which is essentially coupling the data with simulation capabilities. We can couple data-driven models with molecular dynamic simulations or quantum chemistry calculations, for instance, to really drive all of this process. And this can be done by leveraging these specific types of hardware, and this can be done in situ. So we can have operando characterization techniques which are able to respond in real time and to adapt in real time to the type of measure and the quality of the measure that we are obtaining. And this leads to the last part of this presentation, the last challenges, which is how we use all of these techniques, or the combination of all of these techniques, to develop smart instruments, to use this idea of AI as a driving element in the design and execution of experiments that will end up generating this type of self-driving laboratories, right, that will be able to go beyond high throughput and to do the real intelligent generation on demand of data that we need in order to improve constantly the models and to gain new insights in the system or systems that we are trying to model. So overall, I think that we are these are exciting times. There is a lot of opportunities in this area, especially when you are looking at this from the viewpoint of modeling and how models can help to advance research, and the new tools that we have at our hands to really develop these new modeling approaches. And with this, I'm going to finish. Thanks, and I'm getting the control back to you, Todd.
Thank you very much, Robert, and thank you to all of our speakers today. That was really very informative, and we covered a broad range of topics here. Again, if you look at the bottom of your screen, you'll see the Q&A box, and that is where you can type in a question that we can pose to our speakers today. But I think I'd like to maybe start off and ask a question of all of our speakers, kind of covering a little bit from what each of you have offered and provided insights today. And that's, you know, I think we really kind of progressed in a great way. We started off with sort of an understanding of what the rationale and the reasoning behind why we need to make sure that we're collecting this data and developing the framework from which we can continue to pull and integrate. And then we went on to sort of talking about how these, the data that we currently have can be applied to nano and microplastics, and really how do we avoid having to redo or go through the entire process again, launching then into a discussion of how do we build some of the mechanistic data into this. It's more than just collecting data. It's understanding the mechanisms and the dynamics of those situations. And then finally, how do we put all of this data together and learn something from it? And so when I look at this, I just look at the immense weight that it would take to get all of this into a single format. And I guess, you know, my question to the panel is, what do you think is our, you know, sort of our bottleneck at this point for being able to achieve this goal of getting all of this information into a system that can be easily accessible? And then on the other side of that, where are we really succeeding at this, and how can we use those results to push us forward? So if any of you would like to comment on it, that would be wonderful.
I think Andrea should speak, because Europe is actually implementing some of this, I think, at a much rapider pace than we have in the US.
Thank you so much, Stacey. I was just thinking about a clever answer, because I think there is not a single bottleneck. There are several bottlenecks, and maybe my answer is not even complete. But I think one aspect is that currently the understanding of data is still hampered by the fact that we are still lacking data, not that they are not generated, but they are simply not accessible or available to do some meta-analysis or evaluation. So clearly we need a change in mindset that truly the data sets are released, and then still the database landscape is fragmented, and we need more standardized approaches to really interlink this data, to standardize metadata, and so on. So maybe we have a couple of bottlenecks that still need to be worked on in order to make a full understanding even on the wealth of information that we have today, and not also to touch like the quality criteria, completeness scores, and so on and so forth. I think also modelers would appreciate to have a quality tag associated to the data. Yeah, so many bottlenecks, I would say.
Todd, this is Fred. I think that we have to move from the worry of nanotoxicology to a more active nanosafety format. I see that in what has been happening with the dissolution area. Not every test on an official list has to be done, because dissolution means that you don't have to do it. And I would extend that to the type of predictive toxicology that Andre Nell and the colleagues at CEIN were pursuing, and that currently, I think if I'm correct, Andrea, IATA is a version of that is in the Gracious framework. So those are somewhat a flexible response to what is needed for the testing for safety purposes, unless the inflexible response that you have to do a 90-day inhalation study because it's a particle, darn it.
And we've talked over the past, decade or so about, having the journals be one of those key gateways that when you publish, you have to make your data actually available in a format that is usable, instead of just a PDF of your raw data or something, and it's not annotated. So, that we've talked about the logistics of that is probably not feasible, but I think, if you think of the Miami standard for, putting in genomics data, right? That's expected. You can't publish without putting your data in there. So I think we'd have to move to a structure like that to really get the amount of data. And I think one of the key things to that is that there's a lot of negative data that's never published. There's a lot of it. And we're not taking that when we do a risk assessment. We're looking at the published papers and then trying to extract from that, and it just is flipped backwards, I think.
Yeah, and I think that we have a lot of advances. We are seeing a lot of advances, for instance, in natural language processing that can help in doing some of this extraction of the data in some cases, but still, I agree with what has been said. It's imperative to have access to this data, and perhaps having a common format is not that important. The important element is to make sure that the data are well documented and we understand what the data represents, and then we can write whatever type of interfaces to capture the data in the right way.
Thank you all for that. So we do have a couple of questions. The first one here is for Dr. Haas, and it says, what are your thoughts on FDA and international counterparts in regulating nanomaterials, which may affect clinical adoption / use of nanomaterials?
My answer is I don't have any particular opinion on what FDA is doing, but I would like to approach the question from a more general perspective, since I also work in a regulatory institute. And I think regulators also appreciate to have access to this wealth of data from the scientific domain, and to look also at the data that is available from the research. And also in the medical field, it is highly relevant in the preclinical state to have all these evaluations coming from cell cultures and coming from other, maybe potentially biochemical and acellular testing. And I think the way forward has already been paved in the TOX21 initiative. And I think what we need here in the let's say, nano or innovative materials domain is a very similar approach. We urgently need modern and data-driven approaches that are reliable, so that not each and every material variant needs to be fully evaluated again, but we can rely on what we know already and make extrapolations or some predictions that are valid then.
Thank you. Our next question, it says here, playing devil's advocate, this approach of gathering data with too little understanding of the difficulties of evaluating each nanomaterial for toxicity seems to be committing the sin that was seen in biotechnology of drowning in data. How do you think this will actually help the commercialization of new materials? That's to the entire group here.
Maybe I can go first and then the others can add, because currently I do not see a risk that we are drawing in data, but rather I currently see a situation where the problem is elsewhere. So currently not the full data sets are released, and also the metadata description is poor. So that means currently I rather see that it's highly challenging to fully and truly evaluate what has been done, how it has been done, and how it has been evaluated. And that contributes to the situation that we have today, where it is not really clear, like, is that really like genotoxic? Is that really like showing some other adverse effects? Because it's not really clear if two experiments have really been conducted under comparable conditions, or maybe the protocols were just like different. And so all of that matters. And I think currently we would benefit from a universe where more data sets are fully released, where we have a rich description and metadata that we can truly understand what has been done. And then I think Robert will come in with all this artificial intelligence, so you can easily sort out the garbage by using computational approaches. And in parallel, we need to really push forward for quality standards, for completeness standards. And then I would say it like that.
This is Fred. I have a different perspective, shall we say. The regulator is not a scientist. I don't think the regulators are using informatics. I see Andre asked that question. I think when you get a PM in and you have 90 days to act upon it, you go by analogy. You pick the closest particle that you've worked on by analogy, and you move from that, as opposed to saying, I'm going to change how I evaluate this material because of nanoinformatics. It's just a difference in the regulatory nature. So that's why I put it more in the nanotoxicology versus nanosafety perspective. We'd have to ask that people move over to a more dynamic setting of how they evaluate things. And I see that Andre has his hand up. I don't know if you want to respond to what I just said.
I'm not quite sure how we do that, but if it's possible.
It's not possible. Sorry about that.
Okay. Well, then you can accept that everything I said, Andre agrees with, unless he lowers his hand. There's a question from Paul Harton on the Isotab Nano. I just happened to see it. Isotab Nano is a standard at ASTM International. It and other elements were brought together in what's called eNanoMapper. Isotab Nano is a flat file, Excel spreadsheet type. Everything's moved forward with movement in languages. So I would say that eNanomapper right now, in my mind, is an excellent tool. And there's also the MinNano database that came out of CEIN.
Mm-hmm. And just to add to what my colleague said, I think it's important to keep in mind that nanoinformatics in general is not some sort of magic set of capabilities that are going to help us to answer whatever questions we have. Nanoinformatics in general, from data to modeling to data analysis, are a set of tools that provide scientists with additional capabilities that can help them to advance and to look at the data in a different way. And I think that this is the real focus that we have right now. How this translates later on to the use in a regulatory environment, then this is a different question. And this links with some of the things that I said before. If we want to use a model in a regulatory environment, we need to make sure that this model really works. We need to understand how this model has been developed. We need to make sure that this model has been validated, and we need to know where we can trust this model and where we cannot. So there is still a lot of work to do in this space, but I think that the building blocks, which is in part what we have been building in all these past years, are there, and we are now in a position to start really advancing in the field towards this direction.
Maybe if you allow, I can add one more aspect, because I don't know, I think it's also an understanding on who is a regulator and who is rather a risk assessor. But what we frequently see is that we are approached because there are some like journalists out there that read something in a paper. And then they make conclusions on that. And then basically there suddenly is a huge public interest in one of the topics. And it's really difficult to explain what is the science behind. And I think from that aspect, I truly believe that also for this, we need a more open access to all the data, including also the negative data that never will become published, as Stacy just said. And also, like, if you develop or want to develop these modern approaches to get rid of these animal tests that still we need today, agreed. But maybe we don't want to continue to do animal tests forever. Yeah, so then we need the information coming from all these research projects to make use of the power of big data in order to develop AOP or YATA-based approaches that then can truly replace animal tests in a reliable manner. And so this is also something we need to consider here.
So, and kind of moving along those lines to this question, as an environmental health practitioner, I appreciate the reduction of the sky is falling message, as most of us do. Do any of you have any insights into the disposal aspect of engineered nanomaterials and issues that we might face from that standpoint? And how, I guess, maybe how some of the current information that we do have might enable us to make better predictions about ultimate fate?
If I might take that on, since I come from industry, I'd recommend looking to carbon black and the silica industries. Carbon black is 10 million metric tons a year production. Silica is above 4 million metric tons. They've been in commerce, they have disposal requirements, and they would be a starting point for addressing that sort of a question. Second, I believe that our colleagues in Europe are more complete. They connect the safety data sheet disposal to the safety data sheet in terms of toxicity. So it may be that Andrea is aware of, I think it's CLP or something over in Europe, but there's a lot of activity there making certain that the supplier tells the distributor, tells the customer the same information so that it's disposed of properly. And I defer to Andrea at that point.
Well, I'm not sure if I need to answer, because CLP is just the European reality of the UN GIS system that is globally acting. And I think you described it pretty well, Fred.
All right, we have a question here that's probably directed more towards Fred. Are we really documenting our measurements of dissolution, absorption, and toxicity data well enough that we can assess their quality? And I think this a really important question that could be expanded beyond this. One of the challenges that I face as a federal researcher is the ability to utilize other published data and having to have a very well documented QA/QC procedure that goes along with it. And so this kind of, touches on a number of different topics that we've talked about today. But how do we make sure that we're meeting those QA/QC practices when we are doing sort of this big data collection?
I think we're in the middle problem. I don't think that we are getting the right metadata fully, but I also don't think regulators need mechanistic answers from physical chemists on dissolution. I think the need there is more, shall we say, directional. Does it dissolve a lot? Does it dissolve a little? Does it persist? And that would allow someone in the regulatory side to say, what is from my menu, so many from column A and so many from column B are the appropriate tests to apply. As long as eventually you do back it up with mechanisms. I think in response to John's question, it comes more to me as what your test method, open or batch. Are you seeing a possible apparent solubility limit in one system, but not the other? So first, I think it comes down to methodology. And we haven't really clearly established that. I think everyone's doing a lot of work, but I think there'll be, shall we say, some consolidation. And I bring everyone's attention that the NanoHarmony group over in Europe is working on this as a revision of TG 105 from OECD. And I think they are looking at both batch and flow through systems, and they may be the place for more detailed answers to that question.
Yeah, and I would say even, on the tox side, when we think about, studying silver nanoparticles or copper nanoparticles, we do the dissolution studies, but we do it at one concentration, and then we expose our animals over a wide range of concentrations, and we don't really, do dissolution measurements that way. Your thoughts, Fred?
I think there's limits. And so I know that I think it's Kjeld Alstrup Jensen is the person, and Jutta Tenscher are the two people in NanoHarmony, and they're very much involved with what is the dose and what are the concentrations. And the answer is you want to find that apparent kinetic solubility limit to tell you that the particle persists. And just to make sure everyone realizes, in the gracious framework, persistence of the product is what leads to accumulation, which leads to a certain category of tests being done. So you have to identify the persistence or the apparent solubility to be able to make those sorts of decisions, and they are all interconnected. I just don't think dissolution is going to solve all the problems, but it will help you inform you in terms of what toxicity testing you should do.
Thank you. And there have been several questions or calls for making the slides available. The overall presentation will be made available. And so that's what we can offer at this point in time. Another question here, have any rules of thumb evolved as to what constitutes a significant exposure of nanoparticles? The example here is by inhalation and trying to determine if we're measuring what is noise versus signal, but how do we, maybe in the broader sense of that, what constitutes significant exposure? And that would be to all of our panel members.
I think dissolution may give you a floor in the sense that ingestion, oral ingestion, as I used with the lead example, it might be that anything below 2 ppm lead particles is not really a particle exposure, it's an exposure to lead salts, and there's a long tradition of information on that. So there may be in dissolution a floor. I don't know what's a trigger though, or what would be a threshold. And I assume that that's what the regulators do when they do a recommended exposure limit or something of that, or an OEL, and they put that on one of the safety data sheets. But I think that's a very complicated topic, and therefore it comes much later than the current group is being exposed to. So you'll be told, oh, gee, we shouldn't have used benzene when you were a sophomore in organic chemistry. You're going to be told after the fact that some exposures were not particularly helpful.
I think it's really correct. So we need to ask, is the particle persistent? Is it biopersistent? Can it accumulate in tissue? And then the answer will be pretty much different compared to, is it a soluble particle that eventually will become cleared, or is it something that accumulates somewhere over a lifetime? Then you may end up with a significant exposure, even if the initial event or the individual event can be pretty low. Yeah.
And this would all be informed on the toxicology side too. So that would have to be taken into account, like how seriously toxic a particular nanomaterial is.
Correct, Tejal. I'm making the difference between the particle effect and whether the the toxicology of the soluble is acceptable. You might not like the toxicology of the soluble ion, but it may tell you that it's been measured already.
Yeah.
Okay, well, unfortunately, we've reached the end of our time for today. In closing, I'd like to thank our speakers one more time, Stacy, Robert, Andrea, and Fred, for sharing their perspectives and their very wonderful presentations. And it was really a great learning event for me today. Thank you so much. And thanks to all of our attendees who for being a part of today's event and asking questions. We hope that you'll join us for future webinars in the series. And again, we invite you to follow us on Twitter at NI NanoNews and check nano.gov for more information and where you'll be able to find copies of these presentations. So once again, thank you very much to all of our presenters, and I hope that everybody has a wonderful morning, afternoon, and evening. Thank you so much for joining us today.
Take care, everyone.
Thank you.
Thank